Okay, so how is everyone today? Yes? I am. The PDFs are up, but I've gotten behind on the videos, but they all still exist. I'll get them. I'll get them posted. All right. So last time we were talking about improper integrals. I'm going to give you just one more of these. So I could say, please evaluate integral 0. So integral 0 to infinity of, say, something like 2414 divided by square root of x dx, like so. And on all such integrals, the instruction is basically evaluate the integral or show that it diverges. So evaluate or show it diverges. All right, let's consider this for a moment. Diverges. And what that means is, it diverges to infinity. All right. So concerning this thing that we're looking at here, of course, the 2414 is just nonsense, right? It's just some constant. So it doesn't really materially affect what's going on. So let's consider, how does 1 over square root x look when you plot it? So as a sketch, you know, 0 right there and then to infinity. So, 2414, that's a big number, I guess. But as x gets big, square root of x also gets big. So like when x is 1,000,000, square root of x is 1,000, right? So that this would be, 2414 over 1,000 when x is 1,000,000. And, when x is, when x is billions of billions of billions, then square root of x is big, right? So as you go to the right, what will happen? Yeah, this thing that we're integrating is going to get closer and closer to 0. Okay, as you go to the right. But notice that the domain of integration is 0 to infinity. Now, what happens to this as x goes to 0 from the right? Yeah, so let's consider, like, we can consider some number like, say, this, if x is, 0.1234 so that's what, 1/10,000th? No, 1/100,000th, I guess, something like that. And then the square root of that is, that number there. But if we do 1 over that, 316. And then if I insert a few more zeros, which is to say we get even closer, we get to even closer to 0, then now the answer is, 3,000. So it's going to get bigger and bigger and bigger, right? So as a result, this region, what it represents, 2414 over square root of x will, going this way, it's going to get closer and closer to 0 going this way. Like that. Okay, and then going this way, it's going to get more and more, bigger and bigger. Okay, like that. Okay, then the region that we're talking about is all of this. So all of this stuff to the right here. So how far to the right does it go? Right, all the way. And then how far up does it go? Well, how high will it end up going? Right, it'll go all the way up, right? So what I want you to observe about this particular shape here is that in the first place it's not bounded because you couldn't draw a circle around it. Okay, but it's not bounded, but in kind of two different ways. It's not horizontally bounded because it goes infinitely far that way, and also it is not vertically bounded because it goes infinitely far that way. So it's unbounded kind of like in two different ways. So it's unbounded vertically, and it is also unbounded horizontally. As a result, to evaluate this, essentially what we need to do is we need to carve it up into pieces and see if we can make it still consisting of unbounded pieces, but simpler. So we're going to make a cut. So we'll cut, say like right here. We'll cut it at that particular place. And just for sake of argument and ease, I'll say that that's at 1. So if we cut it there, what I want you to observe is that viewing the two pieces separately, like that. So this piece on the left is still an improper piece. Why is it still improper? Because it goes up all the way, right? So it's unbounded above. But it's in a sense better than our previous situation. Why? Because at least it's bounded horizontally, right? At least we have that much. The other piece, the piece on the right, you could draw it like this. Now this piece is also improper. Why is it improper? Right, because it's unbounded horizontally, but it's better than the original because at least it's bounded vertically, right? So, this observation is saying that this integral, if it converges, it surely needs to be able to be broken into these two pieces, right? We could just focus on just that piece and just that piece. So what we're saying is that this thing right here, which is the integral 0 to infinity of 2414 over square root x dx, what this picture is illustrating is that surely this must be equal to integral 0 to 1 2414 over square root x dx, and then what? Okay, so this one would be integral 1 to infinity 2414 over square root x dx, and then what am I supposed to do here? Add them together, right? So this integral corresponds to this picture. It's in a sense, you might say, doubly improper. Okay, we can cut it into two pieces, each of which are singly improper, right? This one's improper because it's vertically unbounded, and this one is improper because it's horizontally unbounded. So now we could evaluate these separately. So, for example, how would we deal with this one? So where's the problem? Right. So the problem is at 0. It's unbounded as you go to 0. So if we were to cut at some point between 0 and 1, okay, for lack of a better name, suppose that we cut it, say, here at A. Then that whole region there is improper, but do you observe that as for the part between A and 1, that's proper? Similarly, this whole thing taken together is improper, but let's cut it somewhere. Somewhere that needs to be to the right of 1, right? It makes no sense to cut it over here. So I'll cut it here at some A. No, A is already there, so I'll use B. Some B that's more than 1. And the whole thing is improper, but the part between 1 and B, that's proper, right? So whatever this is, it's surely got to be the sum of these two integrals, each of which are singly improper. So then we can do the proper the improper integral limit dance with this one, and say that okay, actually what we're going to do is we're going to integrate from A to 1, so just that part, A to 1 of 2414 over square root x dx. That would give us this area right here. And then to get that whole area, what would we need to do next? Yeah, we'd have to say, and now that we know how big it is when A is right there, now we're going to take that A and start moving it toward 0. Okay, so moving this blue cut to 0. And the way you say that is limit as A goes to 0, and specifically we must be approaching from the right. Okay, similarly, by analogy to this one, how do we write that one? Of all that. Well, how else can you approach infinity? I mean, I agree. That surely we're going to infinity from the left-hand side, but you can't go to it from the right, because then you'd be beyond it, right? Okay, so it splits like this. So you can imagine that I could give you some graph, and it makes some shape that's somehow multiply improper. Okay, you have to cut it into pieces which are singly improper, like we did, and then deal with each singly improper piece individually. So multiply improper, because it's unbounded horizontally and vertically, cut it. This one is improper in just one way. This one is improper in just one way. And then we do the limit dance and all of this. So you can imagine that I give you some shape that you have to split into 2 or more integrals. Then the definition of whether or not the limit exists is that all pieces must exist. So for the whole to exist, for this to exist, all pieces must exist. And what I mean by exist is that they must converge to a non-infinite value. All right, so let's consider these 2 pieces, or these. So the easiest situation would be that if we could say that one of these obviously doesn't exist. That would be the easiest situation. The next easiest situation would be if they all exist, but the integral's particularly easy to evaluate. So do any of these obviously not exist? I claim that one of them obviously doesn't exist. So let's consider this one in particular. That one right there. So considering the second piece, which is 1 to infinity 2414 over square root x dx. Well, because the integral is homogeneous, which is to say that you can factor that 2414 out, you could write it like this. So 2414 multiply integral 1 to infinity 1 over square root x dx. And then square root can be written as what fractional exponent? As half, right? So you could write it as negative half, but I want to leave it in the denominator so that it will look like this. 2414 multiply integral 1 to infinity 1 over x to exponent half dx. But aside from this 2414, ignoring that for the moment, that is something that we know. What kind of thing is this? I'm fishing for a phrase that starts with P and ends with integral. It's a P integral, right? That's a P integral. We talked about those last time. So do you remember that we mentioned what is the condition? So in the first place, this is a P integral. P integral with P is what? Yes, so P is exactly half, so it's the exponent. And then what's the condition for convergence of a P integral? Has to be greater than 1, right? So, so this, you could say, therefore, this diverges because P is less or equal to 1. All right. So what does that tell us about the original question? So the whole integral diverges. Therefore, this one diverges. So 0 to infinity of 2414 dx diverges. Because it only takes one piece to diverge for the whole thing to diverge. The reason being is that, well, you could imagine it like this. Suppose that we wanted to paint this. Suppose we wanted to paint it. And then we cut it into two pieces and said, well, if we want to paint the whole thing, surely we could paint just that part and just that part, right? And the question that we're addressing is, will we need a finite amount of paint or will we need an infinite amount of paint? So we take this shape and we cut it into two pieces and then we conclude, well, actually this piece has infinite much paint. It has infinite area, so it requires infinite paint. So is it clear that in fact the whole thing also is going to require infinite paint? Yes?
Could you have started with the first half?
This?
Yeah.
Yes, you could have. In fact, however, concerning this one, so you might ask, is this thing a P integral? And the answer is, it is not. Because if you look at the definition of a P integral, the limits need to be what? From 1 to infinity. So notice that the limits are different. So it looks very much like a P integral. This one does, but it is not. In fact, if you do this one, you will find that it is finite, and it's probably a multiple of 2414. It's either like exactly 2414 or like twice that much. So this piece, in fact, has finite area, but that piece infinite. But it doesn't matter that one of them has a finite, because since that one has infinite, the whole must be infinite. Yes?
So if you change the 1 to 2,
Here, moving this over?
Yeah.
Yeah.
So it will still diverge?
Yes, it will still diverge. But in the end, because, here's the deal, is that, consider what we're saying. We're saying is that this piece has infinite area, right? And then what if I move this blue piece over and cut off a piece, like with scissors, like, then surely because that piece I was formerly talking about had infinite area, so does that, right? Because I only cut away a finite piece. But usually when you make such cuts, it's a good idea to make them at 1, so that you can basically quote the p integral result. Good. Yes?
Is that the only way you can tell it diverges? Or?
No, I mean you can go ahead and just evaluate that. If you were to evaluate this as an antiderivative, ignoring all that other stuff, then you would get 2 square root of x, right? You'd get 2 square root of x. Well, I mean, let's just do it. So this is the answer to the question. But if you were unsure, you could say, well, to do this 1 to infinity like this, 1 over x to half dx, we'd have to play the limit game, so where we cut, and say, we'll view it like this, 2, 4, 1, 4. The limit as b goes to infinity, integral 1 to b, 1 over x to half dx, like so. So now we'll do the thing that's inside of the square parentheses first. So this would be 2, 4, 1, 4, limit b to infinity. So the antiderivative of this would be 2 square root of x. We'll evaluate this from 1 to b. So this would be 2, 4, 1, 4. Limit as b goes to infinity. 2 can remain, well, I'll do it like this. 2 square root b, and then minus 2, like that. So then the question is that, so what just that in the square parentheses represents, that's multiplied by 2, 4, 1, 4. That's how much area there is from 1 to b. And then this limit as b goes to infinity, that's saying, and now let's drag this b to the right. And well, what does square root of b do as b goes to infinity? It goes to infinity, right? So this factor right here is going to diverge to infinity, and therefore this whole limit diverges. So even if you couldn't remember the p integral result, you should still be able to calculate this and determine that it diverges. Other questions? Okay, so now we have a new idea. So integral, so we're in section 8.1 now. And it's called something like arc length. Integral, remember, is that if we have a function that looks like this, so we've got some function defined on the interval a to b, and this is y is f of x. Then what integral is it's the signed area of the shape that's between the red and the graphite. And what we're doing is that we take this shape and we take the domain and we cut the domain into little bitty arrows like this. So a little arrow there. Okay, and then from that arrow we go up or down to the curve as may be. So like this. And then what this does is this makes a nice little oriented rectangle. So the orientation of that rectangle is clockwise, counterclockwise, in agreement with your right hand. So this is a positive rectangle. positively areaed rectangle, whereas the rectangles over here have negative area because you go right and then down, and so that the swirl of them would be clockwise, the negative orientation. Okay, so then what I want to impress upon you is that where calculus is concerned and where this area is concerned, the integral is making the claim that it makes perfectly good sense to view this area consisting, in fact, of infinitely many infinitesimal signed rectangles. So if you were to look at it close, it would, in fact, just be rectangles, if you could just see close enough. And then, we come up with various, we formalize that concept with the concept of integral. And that's really inconvenient because you'd have to actually calculate with infinitely many things and compute limits and what have you. And then the fundamental theorem of calculus is comes to the rescue and says that, oh yeah, because of the fundamental theorem of calculus, actually we have these nice formulas. Okay, so that instead of having to calculate the signed areas of infinitely many rectangles, you just have to evaluate an antiderivative at 2 points, which is incredible. All right. So I want to impress upon you how. To say it, one more time. The calculus point of view of the area of this shape is that it really actually just consists of infinitely many infinitesimal signed rectangles. That's what it is. And I claim that's a natural point of view because, after all, concerning you and me and each one of us, we do, after all, consist of not infinitely many, but quite a few cells, if you could just look close enough. And then each one of those cells, and therefore each one of us, consists actually of quite a few molecules, if you could just see close enough. And our behavior, the behavior of all the objects, us being objects, particularly interesting objects, but objects, is obtained by considering the behavior of each of the constituent components. That's the calculus point of view. Okay, so now we have this different idea. Is that what if we have a curve like this, say, and the question is, and it's going to be, it's not, it starts and ends at a particular place. If you can imagine that this be a piece of string that's not stretchable, then in principle, I hope you can imagine I could grab the end and then straighten it out, okay, and then get a ruler, a linear measuring device, and just see how long it is. Okay, that in principle that could be done. So what we want to do is, given the graph of any function, we want to figure out how long is that. Okay, that's called the name for that concept is called arc length. Okay, so then the way that we're going to build that concept up is in the same kind of way that we built up signed area. So essentially what you do with signed area is you say that, well, we'll make little rectangles. Rectangles that swirl counterclockwise are reckoned to be positive, and ones that swirl that are clockwise are negative. And then we can say that this shape has an area because we will view the shape as consisting of infinitely many infinitesimal of those rectangles. Okay, so then what we're going to do is we're going to start out with the only thing that has length. The only thing that has length, the only way we can measure length in a rectangular coordinate system, like this. So suppose we have a rectangular coordinate system over here, and we've got 2 points, say like this point and that point. Those 2 points right there. But in fact, instead of being wavy like that, suppose it's straight, so that this is a line segment. So that's a line segment there. And because this is is situated inside of a rectangular coordinate system, that means that I can measure the horizontal here and the vertical. And in principle, so delta x, like that, and then delta y like this. Okay, and then if we took those two measurements, delta x and delta y, then the name that we're going to give to this is delta s, for reasons that'll be clear later. And the thing is that this is going to be our fundamental geometric fact that we know. The fundamental geometric fact that we know is the Pythagorean Theorem. So how are these all related to each other? Right. So what we know is that delta s squared is delta x squared plus delta y squared, like so. So that if we wanted to, we could solve for just regular old delta s with a radical. And notably, we're taking the view that delta s has to be a non-negative quantity. So when we say arc length, understand that we're not. It is not the case that something should have a negative arc length. Okay, we don't measure negative lengths. In the end, the reason why you don't measure negative lengths is because well, consider that. Something like this. If you're in the plane. Now, if we were on the number line, it would make sense to give that, to say that it's negative or positive. But if you're on this side, if that's your eyeball right there, and this is your right hand right there, because things are traveling from your left to your right, you might say that that's positive. Okay, because things are traveling left to right. But if you walk over here to the other side and look at it again with your eyeball, and you're not allowed to leave the plane. Again, your right hand is here. Notice that in this case, you're traveling from right to left. So that, in that sense, you'd want to say negative. And as a result of that ambiguity, you don't want to say that one-dimensional things sitting inside of a two-dimensional space can have a signed length. So one-dimensional objects can only have a length, not a signed length. So here's the trick. Here's the whole trick. Is that what we're going to say is we're going to view this curve, and we're going to put it inside of its own plane here. And this curve has a it's sitting on some domain. Okay, and then what we're going to do is we're going to cut up the domain into pieces. So I'll cut it into, just to make the drawing manageable, I'll cut it into 4 pieces. So when you're doing this kind of thing, you always want to cut it into a power of 2 pieces. And the reason is because humans are quite good at cutting things in half, but not in thirds. So if you cut something right in half like this, then that gives you 2 pieces. And if you cut each of those in half, that gives you 4. And if you wanted to continue, you could make 8. Okay, so just like when we were making approximations for the signed area here, we made little rectangles. Here what we're going to do is we're going to say, all right, in fact, the way that we'll proceed is we'll cut these and make approximations with little line segments. So like if we go from there to there, then here is a line segment. Okay, now ignoring all the other stuff and just looking at this part, can you see in the first place that the green is not exactly the red as far as length is concerned? But it's close. But it's not exact. Similarly, we can do this for the rest of them. And so what I'm saying is that this new green curve that we've made, it's not the same as the red curve. It's surely not the same. And the lengths in particular are not the same. But the green curve has the virtue of that it consists of 4 pieces, and we can find the length of each piece. Right? Right? So, to that end, we can view it like this. So I'll say that this is like x0, x1, x2, x3, and x4. Okay, and I've arranged matters. It's not necessary to do this. I could have made these are all evenly spaced, the way I drew it, but it need not, that need not be the case. So these intervals are going to be named after the right endpoint. So this is the interval number 1, because its right endpoint is x1. Interval number 2, because its right endpoint is x2, 3, 4. These lengths I'm going to refer to as delta x1 because it's named after the right point. So delta x2, delta x3, delta x4. Okay, so that's telling us the base of these 1, 2, 3, 4 triangles, right? Because I'm doing this trick on each piece. Now I need to find the heights. So ignoring all the other bits and just looking at just that part, I'm talking about, you know, this triangle right here. And, you know, this is delta x1. I'm asking what's delta y1? Well, this would be, if this red curve is y is f of x, okay, then what's the height of that point? F of x0, right? Because it's input x0 into function f, so that's f of x0. What's the height of that point? F of x1. So, you know, I can say that that I have delta y1 is f at x1 minus f at x0, right? So that's delta y1. Similarly, delta y2 is f at x2 minus f at x1. Delta y3 is f at x3 minus f at x2. And delta y4 is f at x4 minus f at x3. All right. So now we can find the length of each one of those, pardon me, of each one of those green pieces. All right. So if I just write delta xi, so this, I'll refer to each one of these green lengths. So this will be, you know, that green length will be delta S1, this one delta S2, this one delta S3, this one delta S4. So using that notation, I could say, let's see, like this. Yeah. I could say, therefore, delta Si, okay, needs to be the square root of delta x I squared plus delta y I squared, like that. So the length of each little line segment. And of course this is for I equal to 1, 2, 3, 4. All right, and there's nothing special about 4, right? I could have done 44. Okay, it just would have been a lot more writing. Okay, so the idea here is that you know, for any given engineering problem, there's going to be some number of little line segments that is going to be good enough, right? So if we're talking about like you know, like shoelaces, you know, something that's not real super critical, 4 pieces is probably enough. You know, but if we're talking about, you know, like the Large Hadron Collider, you know, you want to be more accurate. But at any rate, there's got to be some number of pieces that's enough, that gives you accurate enough to where we don't need any more pieces because we're accurate to within the width of a proton or what have you. Now the calculus idea is that let's let the number of pieces become infinite. So this length right here, what we're saying is that, in fact, it's got to be, this estimation is the sum of all of those. So you calculate all of those individually, add them up, 4 pieces. But if your engineering problem requires more accuracy, then use 44 pieces. But before we get any further, we need to, we want to consider this. Okay. What we really need to do is we need to look at that and we need to simplify it as best as possible. All right. So in the first place, what we're saying is that delta yi is f at x I minus f at x I minus 1. So, you know, f at 4 minus f at 3, something like that. And there's this thing that we learned in differential calculus 2413, is that if we have a piece of graph here that looks like this, and this is x I minus 1, and this is x I, then conceptually what we're doing on each piece is we're saying something like, well, you know, that red, it's a little bit bendy and wavy, but what I want to do is you know, just connect these 2 endpoints and get a straight line. And we're finding the length of that, we're finding the length of the green. Now there's a theorem that y'all learned, an extremely important theorem, with a picture that looks just like this. So what's the name of the theorem with a picture that looks just like this? Not the Squeeze Theorem. So in particular, it's a theorem that's saying that on this interval here, in fact, there needs to be a point about right here about right there, where that blue tangent line to the red curve is the same as has the same slope as the green. What kind of curve is that green thing called? So this one is called a tangent because it's touching at one point. What's this green one called? A secant. So there's some kind of thing. There's some kind of thing that we need to remember that's saying that you know, if your curve is nice, like this, and you consider the curve, and then you construct the secant. If the curve is nice, there must be an internal point where the tangent is parallel to the secant. What's the name of this result? Starts with M and ends with mean value theorem. Oh, that one, right? So that silly thing, I refer to that as the joke. And here's the it's awful, I'm aware. But that's the point, is that here's the thing, is that I promise not to make the joke if you can beat me to the punchline. All right, so now you're all on notice. It is, I'm aware that it's aggravating, and purposefully so. So what this is saying, this is the mean value theorem. The mean value theorem is saying that there's a CI such that the derivative evaluated at this CI is equal to the slope of that secant line. Well, that's rise over run, right? So that'd be f evaluated at xi minus f evaluated at xi minus 1. So that's the rise. And then what's the run? Well, those two, right? So xi minus 1. But what I want you to observe is that in our previous notation where we're talking about cutting that curve into little hypotenuses, hypotenusae? I don't know how to say that. Multiple whatever. So this is this thing down here is delta x. Okay, and this thing is delta y in our previous notation. So this is, well, let's be clear. It's delta yi divided by delta xi. So as a result, we can solve for delta yi, right? We can solve for it. So I'm going to do that. I'm going to solve for delta. Yi, and obtain that this is in fact f prime evaluated at ci delta x I. And now that means that because of that, I can now plug that into that formula. All right. So now we have delta Si is equal to that, but in fact we can replace delta Yi with that. Okay, so then making that replacement, we have square root of delta xi squared, and then plus derivative of f at ci delta x I square that. Now I can distribute the squaring so that we'd be squaring the derivative, and also we'd be squaring delta xi, right? So that this would look like square root delta xi squared plus derivative at ci squared delta xi squared like that. Then notice that those terms I have a delta xi squared in common. I can factor that out so that it looks like this. So 1 plus derivative at ci squared delta xi squared. Now, this is the product of two things that are in a square root. So square root distributes across product, which means that I can apply the square root directly to that square. And if I take that square out of the square root, then it looks like this. So taking it out, we get square root of xi squared. But what's the square root of xi squared? It is not. It is the absolute value of xi. But now here's the deal. Like on the previous page where we said concerning signed length, but in a plane, because if you take a one-dimensional thing and you look at it from one side, it might appear to be positive, but then you could walk around to the other side, and from that you would then conclude it's negative. That means that it's not. It doesn't make sense to reckon one-dimensional things as having a signed length in a two-dimensional setting. As a result, what we'll do is that when we carve this all up, we will always ensure that delta x I is positive. So now I'll drop the absolute value for that reason. But don't think that it's just for convenience. There's a reason for it. So here we are. So what we're saying is that therefore our estimate for arc length by cutting into, we'll say just into n segments, n of those green pieces, is, well, you take all those lengths and add them up. So the summation from I equal 1 to n of delta Si. You know, so you could like make a spreadsheet. Okay, and you could calculate delta Si for each one and then add them all up. And then if you were making an engineering problem, if you were doing an engineering problem, then you could get close enough with that. But we just got finished saying that that's a nice formula for delta S right there. So this would be the summation from I is 1 to n of square root 1 plus the derivative at ci squared delta xi. Again, this is how you do it with n segments. So that works with n is 4 segments, or n is 4 million, it doesn't matter. And then the calculus point of view is to say that, well, let's let the number of segments become infinite. So the limit as n goes to infinity of the summation from I is 1 to n of the square root of 1 plus the derivative at ci squared dx, not dx, delta x I. So here's the deal. So now I get to make the oldest calculus joke that there is. Because there's lots of jokes. So here's the deal, is that, that thing right there, when I'm saying sum, that's actually a letter, right? From what alphabet? Greek, right? And similarly, this thing right here, that's a letter for, and what letter is it? Delta, and it's from the Greek alphabet. Phonetically, the name of this letter in the Greek alphabet is sigma, and the name of this one is delta. And then phonetically, in English, what sound does this one make? S, right? It's the same as English S. And then phonetically in English, what sound does that one make? It's the same as D, right? So, the longest standing calculus joke is that you take a formula that's got Greek letters in it, and then you compute a limit. And the effect of the limit is to turn all of the Greek letters into Latin letters, because English alphabet is derived from Latin. So, that Greek S becomes Latin S. That Greek D becomes Latin D. And remember that we were carving up an interval. We were carving up an interval into its pieces. And that interval, when we began, was the interval A to B. So there it is. That's the arc length formula. So we don't have enough time to do it right now, but we'll do one first thing next time. And we'll take a situation that says calculate arc length. You have to use this formula. It'll require probably a trig substitution or something silly like that. Okay, so have a nice this day.